I need to know that as well.
Recording. It's recording now. No issues.
Oh, it's recording for you? Oh, yeah, perfect. Yeah. So the first technique, and it's not just a technique, it's a general phenomenon that happens across across topics in math, and that is changing the setting to facilitate computation. Because in maths, most of the times we are trying to compute something and just developing language to make computation easier or something like that to facilitate computation. Okay. This is a general thing that happens. Let's take an example of it which we can understand and appreciate. So it starts with a line in the coordinate plane. So this is the y-axis and this is the x-axis. This is just a grid. This provides a grid like a GPS system so that you can locate a point. That's all. So this is just a system where you can locate a point. For example, when you want to locate this point, and to locate it, you will have to just give the instructions. Instruction number 1 is how much horizontally you have to move. Let's say some 5 whatever unit, and then how much up you have to go. Let's say in this case it is 4. Okay. So if you have to go 5 units to the right and 4 units to the up, then we call it 5, 4. So that's a rule for the GPS system. And there are various other rules, but this is good enough for us. Okay. Now once this is set, then we would like to put a line in this framework. It's like a reference system. We put a line. Okay. Now, last time we had seen that a line has 2 constraints, right? And and one way to see that is like you could give 2 points on a line. This determines the line, isn't it? Once you have 2 points, the line is determined. There is no 2 lines that you can draw. You can only draw 1 line. That's clear. But there is a different information that is also sufficient. So suppose only 1 point is given to you. Okay, and we did not have this line. We just had a point, and this angle is given to you. Okay, let's say this angle. Let's say this angle is given to you. Then this point, whatever that turns out to be, whatever, that's not important. Let's say 2, 4, and this angle. So this point and this angle, these 2 pieces of data is also enough to determine my line, isn't it? Right.
Okay.
So yeah, so here the computation is that how can you calculate this line? How can you calculate this angle? Okay. So because we realize, we appreciate that that's a very important piece of data associated with the line. How do you compute it? It's a very important thing that we want to compute. There are various applications. So how do you compute it? So in what situation? That's the question. So suppose the situation is that someone has given you 2 points, and let's say this is 3, 5, and this. Now if someone gives me 2 points, how do I find this angle? So if someone gives me the 2 points, I know the line is determined and the angle is there, but how do I compute it? So now this is a problem of computing a very important piece of data associated with the line. Okay. Now how do we do it? If just these 2 points are given and this line is not given, then it's quite difficult to know what angle the line will make with the x-axis without going and explicitly computing it. We're not talking about explicit computations. We're talking about computing without actually computing, actually drawing and checking. So how do we do it? So here comes this thing, changing the setting. So we need to change the setting so that we can compute it. So let's see how to do that. So if we bring back the line, okay, the line is back. Now we change the setting, meaning that there is a lot of information present in this zone. So we take this, we somehow try to transfer this angle to that place. Now how do we do this? Transferring an angle is what changing the setting in this case is. So we can do this by taking this line. We could maybe select this line. You take this line and we shift it here parallelly, meaning that we have not changed the angles. We have just shifted the line here. So the line was here and we just shifted it up. The line was below and we just shifted it up. So maybe we could draw a line again back here. So this was the line that was there and we just shifted it up. So maybe I should just, yeah. So we have changed the location, we have changed the setting, and we have transferred the angle. How do we know that we have transferred the angle? Well, because it is obvious, means I don't, proof might be a harder thing, but it's like intuitively clear that this angle must also be that angle. We don't know it, but we know that these two are same. We don't know what it is, but we know that these two are same thing. Okay, so this is my point of first discovering what's important, the important piece of data, and usually in what situations is needed. They will ask you like 2 points are given, then find the slope of the, this called the slope of the line. It's obviously called the slope, means it's not a, it's a natural name, it should be called the slope. And now we have shifted it, we have shifted the angle here, and it's quite obvious that this, of course, these two are parallel, so obviously these two angles must be same. Now it is very easy to compute the angle here, because you could just simply, why? Because that's not a very difficult thing, because here all the information is present. Why? So let's look at this, yellow piece, showing it, this yellow piece. How long, how big is that? That length is, the length is 1, right? Because this, because I mean here you have 3 and here you have 2, so this thing is 2 units to the right, and this entire thing is 3 units to the right, so obviously that yellow piece is just 1. So that's fine, the yellow piece is 1. Now what about this thing, what about this height, this perpendicular length? That is also very simple, because height, oh no, so this is a wrong labeling, like there's just a computational problem here. So it should be 3 here. There's no way it can be 5. 5 will be higher than 4. Okay, and 4 is here. So you see this length again is going to be 1, and that is again quite clear, because I mean this height is 4. That's what this 4 means. The height is 4, and this height is 3, because that's what this 3 means, because all these heights are same. This height is same as this height, so that's 3, and the big thing is 4. So that is just a simple subtraction, and one gets it. So we know that this is 1, and we know that this is 1. But whoa, now since these two are 1, then it's just, so then basically we are looking at a right angle triangle in which the perpendicular and base are both 1, and it's a common knowledge that this is then going to be 45 degrees, because this isosceles right angle triangle, and that, so obviously these two have to be both equal to 45. And even otherwise one can know the tan of the angle, tan of this angle which is perpendicular by base, that is it means tan theta is 1 by 1, which is 1, so theta must be 45. This is our common knowledge, or even intuitively, like if this is 1 and this is 1, so it's isosceles, and hence, but that's a different, that's a, uh, that's something we can even treat it as a black box if needed. But the idea is that we were able to change the setting of where we wanted to compute this important thing. So we changed the setting, but the thing that we wanted to compute did not change, and it went into a place where it was very easy to compute it with well-known methods. And this is one of the examples of this thing.
Okay. So I think this is very relevant for geometry, right? Where you change the setting to facilitate the computation.
Yeah, and this is a very easy example, and very, very important, because there is no way one does not encounter this in class 10, because slopes and equation of line is there in class 9, 10, and so this is always done to prove the formula for the slope. Okay, but we don't, maybe one doesn't emphasize on the underlying idea. Okay. So this is one such example. One can give another example which is slightly more complicated. So should we go on that?
Yeah, for sure.
Okay,
for sure.
the same idea, but means the same kind of idea, but just to show that it can actually be not just in this is quite a trivial thing, okay, but in a more complicated setting, but yet a very relevant thing. A little complicated, but very relevant. So let's see. So again, and it can even be seen as a very practical problem, or even in physics, or even just general. So suppose we have 2 points. One can say like this is a river or whatever, okay, river, and this is your location A and this is your location B. So we are going to emphasize the same thing. We have this location A and this location B, and we want to go from here to here, and but we have to like touch the river and go, maybe because we have to fill water or whatever, we have done hunting, or we have to fill water and then go. So the point is that we have to go to the river, visit the river at any place on the river. I could visit here and go whatever, but I have to just visit whatever, do my work, take the water, whatever, and then go back. Now, and I can do this in this way. I could do this in several other ways. So I could maybe come here and then walk this distance and so on. There are several ways to do it. One can do like this also, and so on. Several ways. Now the question is, so whichever way you go, you have to cover some distance. So if I call this point your hypothetical C dash, because I'm not saying that you pass through that point, but a general such path would look like this. It would hit the river and then go back. So the length you have to, you have to go through, you have to cover some length. This length is C prime A C prime plus C prime B. Now a natural question is, how can I minimize this? The river will not move. This will not move, and this will obviously not move. I have control over this. Where should I hit on the river? What point should I visit on the river and go so that the sum of these two lengths is minimal, is smallest? Like light takes the smallest path, and it's relevant there. Also, in general, the starting point to optimization problem. They're trying to optimize the length AC prime plus C prime. So how do we do it?
Shouldn't it be closest to B? You should touch the river at the closest point to B. That way, or furthest.
Yeah, so both can have their own saying that, but both are not the optimum. Okay, but yeah, but it's natural for someone to think that, yeah, you go to the closest to B, meaning the perpendicular distance. So it's a very bad thing. So yeah, so that's one natural guess to make, like you go so that it's perpendicular, and so that you have to go, but then you'll have to pay the price in traveling this big distance. Right? So that's one way. Or if one thinks the opposite, just so it says that real life problems are not that simple. Sometimes complicated. So it is something like this. So this again, a short-sighted approach. Yeah, he wants the shortest distance in this, but then he has to make up for it in a big one. So it's not obvious what it should be. Okay, but we know that there must be a point where it is the smallest. There must, we know this at least, that there must be a point where the smallest is attained. That is, that maybe one can assume it, and it's clear, right? There must be a smallest point where so that the distance is small. So let's say that this is the point. I'm not characterizing the point. I'm just saying that there is a point. Let's say C prime is the point, such that if pass through that, the distance will be the smallest. Okay. So now again, the problem is of a computation. You have to compute the smallest length, okay? And the setting is obviously not good. It is not helping us to compute it the way it's given. So we need to change the setting. That is the idea. But before that, we must point out one general lemma. So suppose you have a line. Suppose you have 2 points. What is the shortest distance between these 2 points? Obviously, if there are exactly, yeah, obviously. If there are no conditions, this is a straight line. Here, there is a condition, that's why we are not able to. So we need to change the setting so that this condition is removed.
Okay.
And then we'll just follow the straight line path and then do the inverse process and get back the straight path for the original problem. So we'll change the setting. So for that, so first thing in maths is that we get rid of the things which are not important for this. The river is not important. It's only that's important is this is straight, this is a line. Okay, so we remove it. And then we do something, say, can be called a little ingenious. So, and that is, whatever that point is, whatever that hypothetical best point is, you reflect it about, you consider that river as a mirror, like you see where your image is on the river or something like that, and you reflect it. And this is where the setting has changed. The setting has gone from A to A prime. Now, it's a reflection. It's not just any arbitrary thing. So it means, among many things, which are all connected to each other, it means that this angle is going to be this. Naturally, it's a reflection, obviously. So, and also, which is more important for us, but it's the same thing mathematically, is that this reflection is not that good. I should just make it a little bigger. So I can just make it, yeah, maybe this looks better. It's okay. The exact diagram is not important. Since it's a reflection, this length would be equal to this length, and this length would also be equal to this length, isn't it? Which is the most important thing for us. These things are obvious because if you stand in the mirror, I mean, everything on the opposite side is the same. So this is common knowledge.
Right.
I mean, and
Right.
this is obvious. So we know, and this is the idea behind doing this, doing the math. Of course, now this is the basic first geometric optimization problem, which of course is later generalized to a lot of things. But the core philosophy, this idea remains the same. Not a philosophy, just an idea. So basically, the idea is that this is preserved. Okay, so the setting has been changed. Instead of finding AC prime plus C prime B, meaning instead of finding this distance, and I must also label this one, this distance plus this distance, I would instead compute A prime C prime, meaning this thing, plus this. This is where the setting has changed. But what has not changed? The length. The the raw quantity, the raw distance has not. This is not the path I will traverse. You can't walk on river unless you're Jesus. You can't. But the length remains the same, right? And that's important in maths, right? What you're trying to compute, that should remain. So this is like thinking outside the box, thinking in the river. Okay, so now instead of finding this length, I will be finding this length. And this is my point, that we have changed the setting to facilitate the calculation, to facilitate the computation. And the main quantity has not changed. It has changed in a lot of ways. The person is now in the river, but it has not changed in a lot of in the important ways. So now, and of course, my motivation was this is it is an ingenious thing, but if one thinks about it, at least in hindsight, the motivation was to these 2 points. Well, it would have been so good if the river was not there. I would have just walked straight. So we have to just go to that kind of situation, and when you reflect, you kind of go to that situation, because now it is clear that I want the shortest path from A prime to B, right? I want the shortest path from this A prime, A dashed A prime, same thing, that's just a name, A prime to B, right? The shortest path from A prime to B, whatever that shortest path is, that would be my answer, right? So suppose if I go to, if I walk this distance plus this distance, and that would be the same in length walking this distance plus this distance, right? So now I should be concerned about how do I shorten this walk from A prime C to C prime B. But well, that is very easy to just walk straight. I'll just walk straight, and that's it. I'll just walk straight. That is my shortest path. So this is the length that I need to traverse. This is the A prime to B is the length, is the shortest length. Well, why? Because as I showed that for any path I take from A prime to the river and then to B, that would be the same as going from A to this to B, because of the reflection property. Again, this black line and this black line till here would have the same length. Okay. But let's look at it more as a revelation, as a revealing thing then. So suppose I take the straight line, which is the easiest thing, even if you're just making a guess. We take the straight line. Now this is my point. This should be my point. This should be the answer, and this should be the point, right? Because A prime B, the straight line is the shortest distance. So now, and that is attained if I walk from here. If I walk from A to this X and then back to B, because this AX is going to be same as A prime X. AX is going to be same as my A prime X, and then Bx is going to be same as Bx, and A prime B is the shortest distance, and that is equal to A prime X plus Bx. So this should be my point.
So we can say with very high certainty that this is the most optimal path by
Yeah,
creating a
I know. It's not just with high certainty, but yeah, at least even without proof, we can say it with very high certainty. But it is actually the shortest one.
it is actually the shortest.
Yeah, because if there was a shorter one, we don't need to prove it, but if there was a shorter one, then, well, this new red line I've drawn is equal to this. So, and then this is same for both these paths. Then this would have been the shorter distance, but no, this is the shortest one. So this is indeed the shortest one, right? So, but yeah, but there are a lot of course, the point is not to be able to understand each and everything here, but better the more we understand. But the idea is that you change the setting.
Think about problems. I mean, how to think about problems outside the box.
Yeah, and basically, yeah, outside the box, yeah. And then this is used. This is just a starting point. This is used in a lot of very complicated problems, which are quite relevant. Like this can be in very many places, like for wiring, setting of wires and some. So there's one example of this which will not discuss how it's done because it's very more difficult. But it's a very someone is something to think about. Is that I need a point in my, so given a triangle, basically say maybe you can say given 3 cities or whatever stations, whatever, and I want a point such that the sum of the lengths, which lengths? The sum of the lengths from A to this point plus this point plus this point will be the shortest. I want to locate such a point. It's a very relevant problem. And then this can be done by this kind of method. So we change the setting, but it's a little difficult because that needs some rotation and knowledge of that complicated stuff. But yeah, this is the first idea that I wanted to show in this. Okay. Yeah. So this was the first idea, the first philosophy. So if you want, I can say another one, which is a different technique.
Definitely.
Yeah. So again, we'll start with the simplest of the simplest things. Okay. And that is, but here the philosophy is to like a certain processes have. So what the kind of things we'll be discussing here is a certain process will be happening, and it will involve several steps. Okay? It will involve several steps, and those steps could just be addition of numbers, adding one, then adding two, then adding three, and we want to again, of course, make a computation. We want to compute how much have I gained by in after n steps, after 100 steps, what's the result? Give me a formula for it. Okay, after 100 steps. And that's the nature of problems we'll be dealing with. They'll be processed with a lot of steps, and we'll have to we'll be asking for a formula of what happens after the nth step. And the kind of idea that will be used is to study the growth rate, meaning how much change happens at every step. How much change happens at every step, or it could be more abstractly said, how much truth is there at every step. Okay, so this is like induction. If something is true at every step locally, and one step implies the other, then if everything is true, something like that. We'll see it first, not induction, but first we'll see it through a very simple example. And okay, yeah. So this is the idea. That was the kind of.
That would be deductive, right? If every step is true, then the final step must be true.
But yeah, but that is a kind of inductive, right? Like, so you're using using the truths of the first 4 days. Something happened. Yeah. Yeah, like an implication. Right. So yeah. So like suppose there are certain things standing, and they are so close to each other that if one falls, and the next one has to fall. If you know this, if you know that one of them falls, the next has to fall. Suppose you know this first number one thing, and if you know that the first one is falling, then you know that everything has to fall, right? Naturally, there's a bunch of things standing like this. And this can be said in a way that if you want to prove something for all natural numbers, and if you know that if you can prove for nth, then the next one has to be true, just the very next one. So local information. And if you know the first one is true, first statement is true, then you know that all statements are true. So it's like a fire, that's induction. So one falls and it falls, takes the other one. But we'll not do such a thing, problem of such a complicated nature. We'll try to do a more simpler one. Yeah, so let's see. So basically very simple problem. So let's say we want to have a formula for Well, for adding first n numbers, very good thing if we had one, right? Right. Otherwise, you have to just add it by hand. But there is a formula. So the formula is that it is equal to n into n plus 1 by 2. Okay. Let's say we know this formula. Okay. So it means that if you want to add from, I mean, you must have seen this and back. If you want to add these 100 numbers from 1 to 100 without any gaps in the most simplest way, then it's basically, so n is your 100. So you just, this is the answer. Hope that without any work, you can just get it. So we want to know how such a formula can be gotten. So for that, we interpret this thing as a, but there are many proofs of this, many very beautiful proofs of symmetry and all that. But in a simple way, in to highlight this idea, maybe this is not the best example, but I don't find a simple one. So basically, the idea is to view this addition as a step-by-step process. And how will we do that? Naturally, like 1 and then 2, and then adding a 3 in the third step, and then adding a 4 in the fourth step, like this. So we view this thing as a step-by-step process. And after the nth step, we are having this formula. Let's say we guessed this formula by seeing the pattern for first few, or from whatever thing we guessed it. But we want to show it. So now we want to prove that it is indeed true. We don't know how to prove it. But one thing that we do know is that at every step, the information is quite straightforward. At the ith step, at the 10th step, you're going to add the number 10. So let's say this is step 2, step 1, step 4, step 5. So the entire process is difficult, meaning the integration is difficult, but the function is simple. That's what calculus is, rate of change, how much change is happening. This is like discrete calculus. So, so the idea is that the total is difficult to track what is happening overall, but at every step, stuff is simple. It's just adding, just adding the nth number at the nth step. So at the 10th step, for example, so n is just a number, is just a variable placeholder for all numbers, something like that. So at the 10th step, you just add the number 10. Now that we view it as a process, we'll use it to prove this formula. Okay. So I will say, does this formula hold for the number 1? Well, let's see. If there is 1, if I'm just adding one number, then it's just 1. Okay, very simple. And then I should put 1 here and check. Well, yeah, it's 1 into 2 by 2, true. Okay, let me check one more. So let's check one more. This should be 3. And does it follow from the formula? So it means I put 2 in place of n. I put 2 again, of course, and 2 plus 1, that is 3, and then by 2. Oh yeah, 3. Oh, this formula seems correct. So at least we know that the first domino falls. Okay, something like that. The first thing, the first statement is true. There are a lot of statements in this. This said that this is a statement about all natural numbers, right? So I'm just that this part is not so important, but what's next is important. So now that we know the growth rate is at every stage, it's just n, the simplest non-trivial growth. Otherwise, you could say just add 1 at every step, but that's silly. Anyone can say the answer is just n. If you add 1 n times, that's just the definition. But okay, now we'll use the growth rate. So suppose that this formula is true. Suppose I've checked it till 100 numbers. Okay, so let's say the formula is true for 100, meaning that I should give a bit of space here, meaning that this is true. Okay, suppose this formula is true for 100 numbers. We have checked it for first few. No, sorry, shift it. So yeah, suppose this formula is true for the first 100 numbers. Now, since I'm looking at it as a process, the 101th case where we're adding 101 numbers is nothing but adding 101 here, right? And adding 101 here. Okay, this is the key. That since I'm seeing it as a process, as a growth, and I'm focusing on how much is changing at every step, so at the 101th step, 101 should be added. And now I want to check if this, what should be my formula for 101? It should be 101 into 102, means n into n plus 1 by 2. It should be this. Is it that? Can I show it without a calculator here? Let's see. Let's take 101 common. That's a very natural thing to do. and of course the 2 stands apart. The 2 is there. 2001. Oh. So 101 I've taken common. This is just the calculation part, not a very important thing. And now I have 100 left from here, and since I've taken 101 common, just 1 left from here, right? Wait, did I do something wrong? But how will I get 102 then? Oh, no, because yeah, so there's a problem here in the calculation. So yeah. So this is just 100. Okay. Now if I want to add it, I need to first take the LCM. So I forgot to take the LCM. So we have to do that into 2. Now we have to take 101 common. And then of course the 2 will also be there. And then I have 100. And well, then I have 202. Well, 202. Wait, something is going wrong. What? Wait, I'm just messing up a simple computation. So let's just see it fresh. Yeah, so in this, I've added 101, and I want to check that this is what comes. So the idea is clear, but now you want to just check. Well, it should not be very difficult. I don't know why I'm messing it up. So yeah, so let's just take 101 common. Okay, and this part will be left as 100 by 2, and then we'll have this part left, that is 101. Okay, now I need to just take LCMs and so on. So this will just become, will go here. So that will become 100 plus 202 by 2. And this will become whatever, 302, just a second. So this would just become 101 into 302. What the hell is happening? Yeah, this will become 101 plus this, and this becomes this, and this becomes this. All right. Hey, this doesn't come.
But how is that?
Yeah, something is wrong, right? Something is going, I'm just making a mistake in the calculations. I don't know how. Let me just do it for general number n. I might be better at this. So I'll add n plus 1, and then I have n plus 2, and then I have a 1. Oh my god, what am I doing? Shit. Yeah, damn it. So since I took 101 out, I have nothing left here. It's just a 1 here. Shit, what am I doing? Sorry. So this is very bad. So since, I took 101 out, so there's just 1 left here, and I'm still writing the 101 and then wondering what's wrong. So yeah, so now it's very obvious. So just add the 2, and this is this, and this becomes 101 into 102 by 2. And this was the conjecture about in 102, that it should be like this. It should be for 101. The formula should have been this, and which is indeed coming. So by studying the growth rate, I can use the truth about 100. If the statement is true about 100, then it should be true about 101. Okay, formula should be true about 101. But since we know that it is true about 1 and 2, so it should be true about 3. You could do the same. If you could do it for 100 and 101, we could do from 2 to 3 also. So this growth rate is allowing us to push the truth from 2 to 3, and then if it's true for 3, then it should be true for 4. It's true for 4, it should be true for 5. These are all natural. It should all always be true. So we have proved this formula for all numbers, and hence we have proved that this is true. So this was the application of, by studying how much change is happening at every step, and using that to propagate the truth in this string of numbers. Okay. Yeah. Now let's take a more. Yeah.
But what is the basic philosophy behind applying this? Like, this is one type of problem. Is it like following the steps? What is it like? Is it?
Well, it is. Yeah, it is. So this is known as. Sorry, you can say.
Yeah, go ahead.
No, so I'm saying that this is known as mathematical induction. So this is the method that you first check the truth of the statement for 1, and for 1 we checked that the formula satisfies. I checked it. For 2 also I checked it, but it's not important. But I just checked it. So you did that, which means that the first pillar is true, and the second pillar is true. And I also showed that if it's true for the 100th pillar, then it must be true for the 101st pillar. So in general, what I can say is that if it's true for any number n, then it must be true for the next one. That's what I proved.
Yeah. Okay. So just I think I'm getting. But could you just quickly give me a distinction between deduction and induction, just like as a in two sentences, as a quick refresh? Because
Yeah. So
deduction is reduction, right? Basically, it's deducing. It is
yeah,
taking a
a complicated statement, and it is proving that it is true. So like you take an identity x into x plus 1 equal to x square plus x, and then you check it step by step. You should start with the left hand side, you do a multiplication, and you follow some rules of algebra. It is this. Then you follow the exponent rule. It is this, and so you deduce that, oh, now this should be the right hand side. Okay, this is a so you start with a complicated thing, you break it down, or you try to mold it into what is there on the right hand side, or reduce it to 1 equal to 1, something like that. So that's a deductive. Means that if the first thing is true, then the second thing must be true, then the third thing must be true. But it's the feeling is that it's kind of moving downwards. But induction, the feeling is that somewhat it's moving forward. But it's just like it is just the reflect. Both these things is
how does deduction become more true than induction in this way?
no, it's
Like,
not
why is
more.
it more certain?
Why is it?
Why is it more factually? Why is deduction supposed to be more accurate than induction?
No, that's not true. That's not
But
true.
I think induction is generally a generalization, right?
Yeah, it's usually because induction doesn't prove one theorem. It proves a set of theorems. Okay, proves a set of theorems. But I think what you're saying about more true and less true is the problem that inductive reasoning is less true than deductive reasoning. Deductive reasoning is a sure shot. If you're talking about, but that's the difference between deductive reasoning and induction. Induction is just name that we give because it looks like induction. But at the end of the day, the proof of induction is also a deductive reasoning. Inductive reasoning can be fatal sometimes because there's no sure shot in that. There's probability. Like something happens in the first day, you're like, okay, let's see if it happens again. It happens again. If it happens for the first 100, then you're like, oh yeah, it should be true for the next one. But there's a chance. It's still a risk you're taking here, right? So yeah, so deduction is so this is inductive reasoning which people use in our life, and of course we use it to come up with conjectures. But the induction rule that in maths it is that we prove that if the nth thing is true, then the n plus 1th thing must be true. Number one. Number two, we check that the first thing is true. Now here it's 100% guarantee that everything must be true, right? Because if the nth thing is true, then the n plus 1th thing should be true for any n. So if the first thing is true, then the second thing
So what
must
you're
be
saying
true.
is so what induction in maths is deduction. It is
Yeah, it's basically deduction. Yeah, you should not.
okay. We should not confuse the two things. Fine.
Yeah, inductive reasoning and induction are different. I mean, induction, basically the way the people come up with the formula is by inductive reasoning. But when we prove it by induction, that is actually deduction. Okay, we deduce the formula by induction. But inductive reasoning is important because if you don't use inductive reasoning, basically if you don't use confidence, then we can't come up with conjectures. We can't guess things, and unless you guess things, it's not always you can't prove things without guessing things first. Like if you don't have this formula to guess, how will you prove it? Of course, still might be able, but guessing is very important in a lot of times. Right? So in guessing, we use inductive reasoning. We see the pattern and then we say, yeah, it should be true. That is always there. But when it comes to the proof at the end of the day, it has to be a tight proof. And this is the tight proof. But here the main philosophy was that you have to interpret this as a process and the change that is happening at every step. And that change is simple, and that is allowing us to track the thing. Okay. So
Fair.
yeah, that was the thing. Now let's take another example in sets, which because we have covered sets also very.
Yeah.
So I think that can be interesting. That's more of a more interesting example. So we start with the set. Let's say we have this. So we have this set 1, 2, 3, 4. So we are going to count things about sets. So the elements of the set do not matter. It's just the number matters. So let's say this is the set. Now how many subsets can I make? Okay, let's not. I mean, we're not trying to complicate things, but just how many subsets can I make? So one subset can be just an empty subset, right? And the other subset could be just 1. The other subset could be just 2, and then just 3. This is another one. This is another one, and then I could focus on the 2 size subsets, right? So these are all subsets. Right? So there will be many more. Yeah, there will be many more. 2, 3, and then we have 2, 4, and then we have 1, 4. I think we already written 1, 4, and we have 3, 4. Okay. So this was a two-size subset. So already tiring. Now,
Large
yeah,
number.
yeah, it's a large number. Yeah, it's a large number. It's a large number, of course, but it's a very interesting number. That's we'll see. So it's let's list them. Let's list them once. Yeah, so we should have 2, 3, 4. I should have listed them with a good algorithm so that 1, 2, 3, 1, 2, 4. That's the only two, and then you have 2, 3, 4, and then you have 1, 2, 3, 4. There should be one more of size 3, and that is 1, 3, 4. Yeah, that's all. So how many of them are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. 16 is not such a, it's a good number, 2 to the power 4, right? Now, if we suppose we remove the 4, okay, and now if we also remove the subsets which have 4, means that we are basically just looking at subsets of 3, 1 to 3. I'll bring them back, but for the time being. So let's say we remove this and we remove this as well, and we remove this as well, and then we have this. How many are these? 1, 2, 3, 4, 5, 6, 7, 8. Oh, so if there were 4 size, if the set has had size 4, then the total number of subsets was 2 to the 4. If the set has size 3, then the total number is 2 to the 3. This is the inductive reasoning we're trying to use. Oh, okay, okay. We are seeing a pattern. 2 to the power 3. And well, you can now bet that, I mean, this is easy to check. If you had only 1 and 2, then you would have 2 to the 2. So now you can use the inductive reasoning and make a conjecture, right? That if my set had, let's say 1, 2, 3 till 100, let's say, then the number of such small sub objects, subsets should be 2 to the power 100. It's not possible to list them, but it's possible to count them. So this is inductive reasoning. You write, you see the pattern, and you just
But
say,
how do you prove now whether this is actually right or not?
yeah,
Maybe it will
exactly.
break. Maybe it will break down at 24. Maybe. I mean, how do you know?
Yeah. So yeah, that's what we'll try to prove. That's the whole idea of this thing. So here also we'll study the growth. How is it growing? Okay. So let's see. So how is it growing? So we want to suppose we want to count all the subsets of size 4. Okay, these are all the subsets of size 4. Okay, how does it evolve from all subsets of size 3? Where is the what happens so that we go from subsets of size 3 to subsets of size 4, right? So basically we want to see how things change. So subsets of size 4, how do they come from subsets of size 3? That's the change we are trying to look at the step. Size 3, subsets of size 3. So first thing is that if you have a subset, all subsets of size 3, they are also subsets of size 4. I mean, not subsets of size 4, subsets of 4, subsets of 1 to 4, right? Subsets of 1 to 4. And yeah, so I'm saying this is slightly, like, you could say abuse of notation, but precisely it's wrong. It is wrong. So here suppose we have subsets of size 3, and we're trying to again looking it as a process of going from 3 to 4 to 5 to 6, and then joining everything and finding the number. Subsets of, again I'm saying size, subsets of 3, 1 to 3. And what's the gap? How do you go from here to here? Let's see. So first of all these subsets of 1 to 3, they are also subsets of 1 to 4, right? So whatever number this was, whatever number this is definitely there, right? So that is uh, one part of this has been identified with a smaller class. Okay, so we are understanding the growth a little bit. And what are those objects? So these are definitely there, subsets of 3. and definitely these anything which doesn't have a 4 doesn't have a 4. So this is definitely there, and then this is definitely there. These are nothing. So these were there in subsets of 3, 1 to 3. Okay, and these have been carried over to subsets of 1 to 4. That's okay. What? How did the other things come? Can we connect it with the just the previous step? So to study the growth. So the other things came. Like how did this come? This came by adding a 4 in this. So this is connected with this, right? This is one of the connections with the previous thing. And how did for example how did this come? Oh, the 4 is here, so it must have come from here. Means you can connect it with this. So everything which has a 4 comes from something which did not have a 4. That is induction. Means basically the growth. It came from this. And how did this come? I should not draw extra lines. This came from this. And similarly, how did this come? This came from this. By adding a 4. How did this come? So this came from this by adding a 4. Similarly, there are other things like this. By adding a 4 to this, you come to this. So everything, I added a 4 in it, and I got it. I got the thing which has a 4. Similarly, yeah, I think I covered everything. So in this the making of subsets of this is nothing but two kinds. Number one is subsets of 1, 2, 3. Okay, let's say whatever size. So let's say there are x of them. We know there are 8 of them, but let's say there are x of them, or let's say there are 8 of them. There are 8 of them. There are 8 of them. So yeah, 8 of them. And the second species, the second type of objects are those which came from 1, 2, 3 only, subsets of 1, 2, 3, but just that you added a 4 in them. So these are eight things here, or eight things. You just that you added things inside the set, but the number of sets is the same, right? So there were 8 things in this subsets of 1, 2, 3, and in each of them you just added one thing, but the number of subsets is the same, right? So this is also 8. So we know that there's a doubling going on, right? Subsets of 1, 2, 3, one copy you just put, and in another copy of subsets of 1, 2, 3, you put a 4 in each of them, and that. So basically, subsets of 1, 2, 3, 4 is basically 2 copies of subsets of 1, 2, 3. So that's the growth. 2 copies. So it means that answer for this must be 8 plus 8 plus 8, or rather 8 into 2. So we understand that the growth is 2 times always. So it means that since subsets of 1 and 2, there are four subsets, and so subsets of 1, 2, and 3 must be 2 times of that, so it must be 8, and subsets of 1, 2, 3, 4 must be 2 times of that, 16. So I'll write this at 2 to the power 4. And if you want subsets of 1, 2, 3, 4, 5, then by the exact same reasoning, it should be 2 times of that, so it should be 2 to the power 5. And similarly, if you want to find subsets of 1 to 100, it should be 100 times of, it should, you do 1, 1, 1, you go to the power 6. And by the time you reach 100, you'll have 2 to the power 100. And that's how we prove it. And for any n, it should be 2 to the. So again, the growth was simple. How did it grow? How did subset of size 4 come from? Can we identify them as coming from subsets of size 3? And that led to this beautiful.
So we basically found out that there is a doubling going on with every added element in the set.
Yeah, exactly. With every added element, whenever you add, there's a doubling going on. There's a 2 multiplied. So in the power, it will increase. Power of 2 will increase by 1. And since the start was important, but start is usually very simple to detect, very simple to describe, and the change is a little hard part, but we described it very nicely. And the change is important. So the change helped us to know. So basically, the idea is that once you know the rate of growth of an object, and if you
Once
can
you know the rule by which it is growing.
yeah, exactly, the rule, you have to come up with your own good rule, and so that once you know the rule, then and then you integrate over that rule. That's what we are kind of doing. That's what integration is. So the area, to find the area, they split it into a small thing, and this is the rule, rate of growth, and then they just add this over entire thing, and you find the area of the entire thing. But that's a much more complicated thing to explain. But I think this, for discrete maths, this is the first proof. Very, very interesting. Like 2 to the n. Okay, 2 to the n actually suggests that at every stage it should have multiplied by 2. So that's the, if you think in hindsight, it should have been like that. Otherwise, how will you go to get 2 to the n? If it's for 2 to the n minus 1 in the previous step, it has to get multiplied by 2. So that's the beautiful thing. So this was the second strategy, second problem solving strategy. Okay. Um, yeah. So I think today we shouldn't start anything more. So maybe I can tell one more strategy if you want, like this.
Yeah.
And
Yeah.
it
Yeah.
will also be very simple to understand. But yet that will be maybe
How
more.
many are there in total? How many are there like this in total? Like, what do you? I mean,
It depends on
like,
how you categorize them. Someone will say that all this is same, all is deductive reasoning. Okay, but
what are
in
the
general,
types
yeah,
of reasoning that?
but the really ones which are really different, I would say that there are like eight or nine. I like to keep it like there are 8 or 9 which are like I couldn't have invented one of them from the other, so I like to call them different. Okay, so one of this is the growth thing that is definitely there, and the one that is changing the setting. So when we were changing the setting, we were not really changing the object. Right? We're not like twisting the line and making it a circle. We didn't do such things. Right? That's another very important one. That's like radical changes in the structure, but it still preserves something. But that's even more powerful because radical changes means that you can simplify radically. And if you're still not, and still the interesting things are not changing, the things that you are interested in in that problem, if they are not changing, then that's really a powerful thing. So there are things like inversion and
Just
sort of.
quickly, without going into details, could you list out the 7, 8 ones which are important? Like, can we just like make a list of those rather than go into any new one? That
Yeah,
at least I'll get top level view of what are, like we've covered one. The first one was
changing the
changing
setting to facilitate
changing.
facilitate computation. Okay. So that was the first one. And the second is studying growth rate growth studying growth rate. Now you can call it anything,
A,
induction.
induction to find a common rule
Yeah,
essentially.
induction to find a common rule, studying the growth rate of a process, or a local global principle, local change, studying whatever you can say. Another
I mean,
third
these
one.
are all interesting terms. You should write it. And the third one would be
Yeah, the third one, which is really different, is invariance,
okay.
which kind of you could say is a combination of these two. Okay, but it's still quite distinct, has a very distinct flavor. So invariance for
Would inversion come as one of the processes as well? Would inversion come as one of the processes, like
no,
problem solving?
no, inversion is inversion can come. Yeah, inversion, it comes more generally in something called reverse engineering.
Correct, correct, correct.
Yeah, and that's actually a proper branch. Engineers, those who study certain branches, they actually study it as a proper like course, not just a. But yeah, reverse engineering is of course one of the strategies. But it usually it's not good. It's not. But that's more like a general philosophy. That's not very specific thing. But invariance is a rather very specific thing. So invariance is what happens is we have a very chaotic thing. A lot of changes are happening. That the main thing is that a lot of changes are happening, not some very structural change like this. A lot of changes will be happening. Okay, and there'll be a lot of freedom to make the change, to destroy the structure and to change, but still there will be some point which will not move, or some, what you call, something will
So this
remain
is
even. Yeah,
the opposite of variable, invariable,
yeah,
invariance. That's
yeah,
the
something which doesn't change when there are a lot of changes, when there is apparently a chaotic system going on, but something does not change. I think this is one of the very important problems of this strategy. So there's a puzzle behind this. Like if you have numbers on the board from 1 to 100, okay, and you decide to pick two any random of them. Let's say you pick 3 and 70. You rub them out and you write their difference on the board, and you write the rest of the numbers also. Number of numbers has decreased by 1. You took 2 numbers and wrote 1 number. Now you pick any two again, and you again write. You take the difference and you write it, and you keep doing it. Now the claim is that at the end of the day you will get an even number, or I think it's an odd number. I don't remember the exact question, but you'll get a fixed, and it will be even or odd. It can be set. So the parity is not changing. That is the invariance. Okay, Something will not change at the end of the day. Now, the strategy behind this kind of problems is that, well, spotting that something doesn't change globally is quite difficult. But at a particular step, you can still find the invariance very easily. And the why invariance works is that if something doesn't change at one step, then it won't change after 100 steps also. But it's easy to spot that it doesn't change in one step. But it's not. And that will imply it doesn't change. And so that's where you apply the induction on it. And but to guess the what does not change, that's the art. That's the craft rather, where what doesn't change and what you should be looking at which it doesn't change. And there could be many things which are not changing, and they may not be useful to solve the problem. So invariance is a really interesting. And then there's something called spatial reasoning, or that's called the pigeonhole principle. Okay, meaning that, I mean, if you have finite space and if you want to put a lot of things in it, like finite number of boxes, let's say you have 10 boxes, and if you have 11 things to put, one of them will have to have two things. Right? So yeah, or this can be said in a more better way, is that if you have n pieces of data, in statisticians will say that if you have n pieces of data, and suppose the average is suppose you have 1 to whatever, some numbers are there, some random numbers, 2,000, 4, 5, 4, whatever, 1,000,000, whatever you have, and you took that average, and let's say the average turned out to be 50, then there must be one data from here which must be less than 50 or equal to 50, and there must be another data which must be bigger than 50. It's quite obvious, because everything was less than 50, the average would have been less than 50. But it's obvious, but it's quite powerful sometimes. Okay, and sometimes it's not easy to see which are the pigeons and which are the holes. You have to see that in a problem where there are numbers and there are graphs and there are people. You have to see which one should be how should I arrange the things, and how should I fit the pigeons and the holes so that I prove. So this is the, I think, very different principle. Okay, and well, there are many others, I think. So there is one called the coloring principle. So where this more has to do with arrangements. So can you so if you have a chessboard, can a knight start from any point and go any point by visiting every point exactly once? So questions like these, or suppose you have a 8x8 chessboard, and if you have those dominoes. So one day you're bored, and you just have dominoes and 2x1 let's say 3x1 that's more interesting, 3x1 dominoes. And if you have a 8x8 chessboard, but there's no one to play with, so you play with these two things. So you take these 3x1 dominoes. 2x2 dominoes are very not interesting, because you can obviously tile this with them. But if you have 8x8 board, and then you can start with trying to so you can start filling up this 8x8 board by 3x1 dominoes. Now, can you prove that you cannot do it? Tiling means that, of course, tiles means that you can't overlap. That's not a tiling, of course. But there can be generalization, but usually tiling means that it should not overlap. So without overlapping, can you fill the entire board with 3x1 dominoes? How do you do it? So there you use some kind of coloring. So you color the board in different innovative ways, so that something will not be. That's a little complicated to explain.
These are fairly advanced kind of problem solving techniques, right?
Yeah, and then of course, which I forgot. Yeah, and then there's something called algorithms is of course there. I mean, so you treat the problem as an algorithm, and you so like one of the techniques in algorithms is greedy algorithm. So you try to have to optimize something over a big space. So you try to optimize it at every stage. You try to take the best possible thing at every stage and hope that will give you the best possible overall. But there are some other constraints. So usually that doesn't work out, but it works out in many situations. So that's a greedy algorithms or whatever. Yeah. So there are a lot of, so these are more non-mathematical strategies. These are the more non-mathematical strategies, so solve problems. The more mathematical ones are, I think, a little more abstract, where it says like, there you do things like, you put a support. They're not very relevant for us. So there are things like to study some object. So you have to study the set of all. Suppose you have to study the set of all subsets only. Okay, set of all subsets. So you put those subsets in, you arrange those subsets. So you put the empty subset here, and you put 1, and then you put 2. This is another subset, and then you try to put an order between the subsets. Try to create a hierarchy class in the set of subsets. Okay. 3 comma. So this is a natural hierarchy. The 3 comma 4. It's not very outrageous to say that 3 comma 4 is bigger than 3 and 3 and 3 is bigger than 3. Right, and it's also okay to say that it's bigger than 4 because it has 3 and 4. So you build up a kind of order in it, like we have order in natural numbers. Something is bigger than the other, but sets don't have or you can't arrange the set. But people try to do that. Once you arrange it, you have given a structure to this. Okay, now to show that something cannot be done, you try to show that if that thing can be done, then this structure has to be violated, and so it cannot be done. So you not just so you give a structure to sets, and that gives it more power for getting contradictions and proving some properties. There are many things like this, but these are, I think, one of the.
I mean, is there anything that specifically helps us solve word problems and things like that as
Oh
well?
yeah, word problems. Word problems. I don't think there is anything special in word problems.
You just have to basically learn the meaning
Yeah,
of the
yeah.
words and break them down. I mean,
Yeah,
they're
I mean
basic.
everything is a word problem in some sense, right? All these are word problems. So that is that word problem is basically just practice and basically mathematical modeling. How can you convert a problem into equations, and that's more like a linguistic thing. Like you read and you understand and you
More basic.
convert
I
it.
mean, it just comes with more familiarity.
Yeah. But that those things are easy. Once you convert the word problem into mathematics, then it's very interesting. Like how will you can you see subsets as a binary sequence and do it, or can you see binary sequences as a tree and do it? A lot of things like that. There comes the hard part. So yeah,
I think this gets fairly abstract, right? I mean,
it gets abstract,
there-
but one has to but there are a lot of examples, and the way the thing is built, people do it. So it's not like it's not it's abstract, but that's because when you see it everything in one day. But once you do it along with examples and with practice, they have a lot of power. Practice and examples, then it comes naturally. You get used to it. Even then there will be times where it will seem very very abstract and too uh, yeah intimidating, but it comes with examples and all, and because we have a lot of potential in our brain, in our head, right? So when we study it, it becomes easier.
so the fact that we figured all this out means that
Yeah,
there is a
yeah,
lot
we
of
have the potential. It's just that we're not able to tap it. So math, once with the right examples and all, like now I find some of these things natural, and I still don't find a lot of things natural. So once I practice it, it comes. But of course, different people have different capabilities. I still don't understand a lot of things. But yeah, but these are natural things. Like if one starts doing it and taking examples and relating it, and then it becomes natural.
the effort is in the practice, I guess, for maths.
Yeah,
That's
you have to
the
practice. And yeah, these are actually not too abstract. These are quite relevant things. Some of the things are, yeah. That is it.
all right. Shubham, you can like switch off the recording. I mean,
Yeah, I should switch off the recording. How do I switch it off? It's very good. So was I recording it?
yeah,
Oh
this
yeah, I
is
was
recording.
recording it. Yeah.